in there that Dave Newcomb put together that has been shown countless times since then to kind of give you a general idea of what a perpetual pavement looks like. On the left-hand side, you can see kind of typical depths of pavement layers. So anywhere from about 8.5 inches thick to maybe 10 to 14 inches thick of total asphalt concrete. And the idea of these different pavement layers is to very carefully select, design the asphalt concrete layers and the thicknesses to meet different kinds of stress conditions through the depth of the pavement structure. So near the surface of the pavement, where we have high shear stresses, high compressive stresses and strains, we need to have high quality asphalt concrete materials at the very surface. Maybe that's an SMA, maybe that's an open graded layer to provide good drainage, good safety conditions at the surface of the pavement. Deeper in the structure, high modulus rut resistant materials. Here we can maybe take advantage of increasing the wrap content to be very rut resistant. There's all kinds of options that you have at those depths. And then towards the bottom of the asphalt concrete, we need to recognize that that is where most of the bending or the highest tensile stress and the highest tensile strains are occurring. And we need to think about that and maybe select pavement layers and materials to resist that. And so we would refer to that as being fatigue resistant. Again, that's where we have that repetitive bending action, and we want to eliminate cracks that may initiate at the bottom of the AC and propagate towards the surface of the pavement. All of that needs to be built on top of a strong pavement foundation, and that's kind of a vague term, what constitutes a strong pavement foundation. We want to design that foundation in such a way that we're not going to see rutting occurring down in those deeper structural layers. So whether that's through, if you have a weaker material, maybe through cement or some sort of stabilization, fly ash, something like that, lime stabilization. We could build a perpetual pavement on a full depth pavement right on the subgrade. Maybe we need to have some other unbound or lightly bound granular materials there. But the point is that we really want to design it in such a way that we don't have deep structural distresses, we don't have cracks that initiate at the bottom of the asphalt, and then all we're looking at is sort of a sacrificial upper layer that as that ages and as we get maybe top-down cracking, we can mill that off, maybe even replace it with the very material that we milled off, and we have a brand new riding surface. And these have been shown through economic studies to be very, very efficient in terms of life cycle cost analysis, very, very efficient pavement structures. So how do we go about designing a perpetual pavement in an ME framework? How do we arrive at those thicknesses? Well, we have to think about the pavement layers in terms of, and we have to make an initial guess at what the layer thicknesses ought to be. That's the thicknesses D1 through D4 you see in the diagram. And with that, we have to also define how stiff each of those different layers are. So we term those E. So the modulus of layer 1, modulus of layer 2, and so on. Within a mechanistic framework, we can simulate a loading event in terms of how heavy the tire is and what that tire footprint looks like. And we can use a computer model to then make a prediction about the amount of tension we see at the bottom of the asphalt layer and the amount of compression we see deeper in the pavement structure. And all of that is what we would call the M part of ME design, the mechanistic part. It's just putting in a pavement structure, computing stresses and strains. The empirical part comes in on the right-hand side of the screen, where we have to think about, well, what relationship do those strains have with how many load repetitions we will expect before we see a crack develop or we see a rutting, critical amount of rutting form. And so this the slanted line here, we usually refer to that as the transfer function, and that relates the amount of tension or the amount of compression to how many load cycles we have until failure, and that's what this log n, that n is the number of cycles until failure. Within perpetual design, we also need to recognize that we have a threshold strain, and that threshold strain is important because that's the point below which we will not see cracks develop or we won't see deep structural distresses like rutting occur. So if we design it in such a way, if we choose the thicknesses to be on the thin side of perpetual, then we'll have a finite number of loads until failure. But if we can design in such a way, once we know where that endurance limit is, we can design it to be just thick enough to be below that threshold strain so we don't have any damage accumulation. In fact, when we do this, we essentially have an infinite life with respect to fatigue or with respect to rutting deep in the structure, because we can put as many loads as we want on there. It's just not bending enough to create a problem. It's sort of like if you were to have a paper clip and you just bend it a little bit. You could do that for hours and hours, days and days, and it'll never break. If you increase the amount of strain or the amount of bending, eventually you'll have it break apart. So that's what we're trying to achieve within ME Design. And this is really what the PerRoad software is meant to do. And as Trenton said, what we're trying to get away from is getting away from a single threshold response, that dashed line, and think about a whole distribution of pavement responses, and that's where we're getting to. So it was about 45 years ago that Professor Montesmith at Cal Berkeley sort of theorized and postulated that most asphalt mixes should have an endurance limit of around 70 microstrain. And about 30 years would go by before that was really that theory was put into practice on the I-710 project in Southern California. And that pavement was designed and built to be perpetual at what we now know to be a very conservative number, but he was right, a very conservative number of 70 microstrain. In 2002, when the Asphalt Pavement Alliance began to promote the use of perpetual pavements and began to really develop the design guidance for perpetual pavements, they were promoting using 70 microstrain. In 2007, there was a big NCHRP project, 9-38, that was conducted between the Asphalt Institute, University of Illinois, and NCAT. They found in that study that for unmodified binders, a good conservative number for a threshold strain for cracking was 100 microstrain and 250 microstrain for modified binders. There was also some recognition in that study that the laboratory condition, which is shown in the picture on the right, where it's just the typical bending beam fatigue apparatus, that condition in the laboratory is much more severe in the field, and I'll talk more about that. But that kind of leads us to this idea that if we're designing in the or if we're using a laboratory condition to try to predict what's happening in the field, that'll lead us towards non-optimal pavement sections. So in 2007, when the first kind of earlier editions of the MEPDG came out, it was recommended to use between 100 to 250 based on that NCHRP study. And then more recent work done here at our NCAT test track by the work part of Dr. Richard Willis's doctoral research found that our field measurements were much higher than what the endurance limit would have us believe coming out of the laboratory. So this is a graph from Dr. Willis's dissertation and some papers that came out of his work. But these two sections, sections N3 and N4 at the test track, the blue line shows what the measured endurance limit was for those two sections. It was about 150 microstrain for both of them. And the two lines, or the two curves there, correspond to the measured strain levels in the field in those test sections. And these sections were shown to be perpetual. They never developed bottom-up cracking after 30 million ESL, and we finally took them out of service. But what was interesting about these curves is that somewhere in the neighborhood of 60 to 65% of the time, the measured strain level in the field exceeded the endurance limit, and yet we didn't see bottom-up cracking. And that kind of formed the basis of this idea of not designing for a single strain level, but designing for an entire strain distribution. And that's what I'm going to be driving toward here in terms of the software modifications. So that work was done as part of his doctoral work. We did some additional research looking at a whole host of sections, and what these curves are showing is not just sections N3 and N4, but for a whole group of sections at the test track. And what's interesting is there's a gap between these strain distributions, and this gap is sort of a break point between those sections that had bottom-up cracking. So these curves over here, the three to the right of this horizontal arrow, all experienced bottom-up fatigue cracking. Those to the left of this arrow did not experience bottom-up fatigue cracking. And this, again, is now forming the basis of, well, we ought to then be able to design on the basis of a strain distribution, recognizing that it's higher than values measured in the laboratory. And you can see the references for several papers there if you want to dig deeper into kind of how these distributions were developed. So this kind of brought to the forefront the idea or the need that we should have distribution-based design, not a single strain value. And the reasons for that are that pavements experience a very wide range of loading and environmental conditions in the field. In the laboratory, we run the test at a single test temperature, at a single strain or stress value. We just flex that back and forth with no rest period, no temperature cycling, none of those conditions. What we see in the field, however, is we have wheel wander of the trucks, we have varying load levels, we have daily temperature cycling, seasonal temperature cycling, we have rest periods between loading events. When you put that all together, what we get is really a wide range of strain responses. We don't just load it at a single value. Maybe we do that in a heavy vehicle simulator or other kind of very restrictive kind of testing condition, but in the real world, pavements experience a very wide range of strain responses. Another point is that traditional mechanistic design uses transfer functions and Minor's hypothesis to sum damage over time. And I really didn't get into the Minor's hypothesis when I talked about mechanistic design, but it's this idea that we can sort of sum damage over time. One of the big problems with executing design within an ME framework is that you're very dependent upon the transfer functions. And there's been a lot of studies done both in the laboratory and in the field to try to calibrate. In fact, if you're using the ASHTOWare Pavement ME software or using the MEPDG, it's highly recommended that you calibrate the transfer functions before you use it to account for local conditions, local materials, and so on. But one of the big problems that we face with those transfer functions is that they're not widely applicable, and sometimes they're not terribly accurate. Our own work at the test track has shown that in some cases, even when we go through a calibration process, we're not able to accurately predict fatigue cracking in the future. And so one of the nice things about using a perpetual design is that really transfer functions, if we just rely on measuring the threshold strain levels and then relate that to field performance, then we really are able to sidestep the transfer function idea and just try to design so that it doesn't crack as opposed to predict when it may crack in the future. And that's kind of the third point on the slide there. Designing with a strain distribution will limit fatigue cracking, will limit rutting, and help us to avoid transfer functions. And it'll also, as I'll show, will help us arrive at reasonable perpetual or maximum pavement thicknesses. So some more recent work was done because Dr. Willis's work at the test track was based on measured strain levels. Some of you do work looking at measured versus predicted through computer models, strain levels. And what we're finding is that we needed to kind of adjust the control strain distribution to take into account that when you're designing a pavement, you don't have instrumented pavements, you just have to make a prediction. And so some more recent work led by Dr. Nam Tran at NCAT and supported by a number of other NCAT researchers, basically looked at the original, what it says here, the field fatigue limit, the dashed line, and reran all those sections and developed this black line to be able to, based on PerRoad simulations, to be able to predict when bottom-up cracking may be a problem. And again, there's a reference for you if you have interest in digging deeper. We also were able to tabulate that limiting strain distribution, and so you can kind of think of this as developing sort of an upper limit for strain-based design. And so we've got it laid out here in basically 5% increments, and so here's towards the maximum is 326 microstrain in tension. The average is around 100, and the minimum is down around 21 microstrain. And so you can start to think about this table, the first two columns of the table. If you're designing a perpetual pavement, you want to be at or below, in terms of strain levels, at those percentiles. One of the other things that came out of the work was to recognize that not every mix that we want to analyze or use in the field is exactly like we have at the test track. And so through work that Dr. Willis did, and then later Dr. Tran's work at NCAT, we're able to develop what we call these fatigue ratios, where you take a laboratory number, let's say 500 and something, or 150 or so microstrain, and then multiply by these strain ratios to determine what the strain should be at a given percentile. So this provides us a means for design. We can either use column 2, which is the the field determined strain values, or if all we have is a laboratory determined number, we can multiply by these values to come up with what the strain level should be for our controlled distribution. So it gives us a little more flexibility. So everything I've talked about so far is really, in terms of those strain levels, was based on NCAT test track data, which is good, but it is it's one climate, one set of loading conditions, limited set of materials, and so on. And so we wanted to do a validation study to look at existing perpetual pavements, perpetual pavement award winners, as an extension of this earlier work. And so what we're able to do was find a number of perpetual pavements from around the country, and you can see the pavement cross sections here, a wide range of pavement conditions, a wide range of states, and essentially analyze those with the best available information and see how do those stack up against these the strain criteria that we developed out of the test track. And this is just very recently. In fact, the work is in press. Alfredo Castro is the lead author on the paper. He's one of the grad students here at NCAT.
Dr. Tim, this is Amy. I was going to leave all the questions to the end, but here's a question I think would probably be appropriate to ask right now based on 2 slides back. The question is, I'm confused by the percentile. Is the percentile related to the expected loads, the expected strains? Can you talk about that for a minute?
Sure, yeah. Let me go back here. So let's just look at this very simple example of 2 sections of the test track. So essentially, if we're designing a pavement, and let's just say the dark solid line is our cumulative strain distribution, and let's say that is going to be our control. What I need to do as a designer is design my pavement so that, let's say at the 90th percentile, I need to be at or below, so it's around 300 and maybe 25 microstrain. I need to be at or below that value for it to be perpetual. If I'm on the right-hand side of it, it means I have an expectation that there will be bottom-up fatigue cracking at some point in the future. So we think about this, and let's just say this is our control. We think about this control as being the break point between, on the left, pavements that don't crack, and the right, pavements that do experience bottom-up cracking. I'm not sure if that answers the question or not, but I'll circle back to that as I get into the design software.
Hey, Dave, it's Rutting real quick. The other part of the question where you have the vertical blue line.
Yes.
If I understand correctly, if this is the only value you have, and it looks like it's about 160 microstrain.
Correct.
That second column, you multiply that 160 by those percentages, or by those values, to basically reproduce that
Correct.
Distribution curve.
Correct. So yeah, that's a great point, Trenton. And so I would take 160 for my mix, multiply by this column, and what that does is establish for me a mix-specific distribution curve. That's exactly right. And so what that allows you to do is to take into account a wider variety of materials. If you're using just the NCAT distribution, then you're locked in on this single distribution. Something else to point out with these grayed out boxes, what we found, if I go back here, is a tremendous amount of overlap between sections and so on. And so what we've really decided to focus on in the software is just above, essentially above the 55th percentile. And so you'll see in the software that we're really focused on this area where the 2 sets of curves really diverge. All right, so I hope that answered the question. I'll come back to it again when I show how that's put into practice in the design software. So back to these other sections from around the country. This table shows, again, the states that we pulled from, and these all happen to be interstate pavements. They tended to have better records in terms of traffic, construction, and so on. And the year that it was selected as a perpetual pavement is column 3, the number of years in service. So some of these, I think we topped out at 44 years, and the youngest was 35, and some considerably high ESOL counts. And again, these pavements did not ever have bottom-up cracking, deep structural rutting. All they could have had would be just minimal amounts of structural improvements over time, dealing with just issues at the surface of the pavement. This graph has a lot going on. Again, it's from that TRB, the recent TRB paper, but what I want you to focus on is the dark black line is the control distribution that was developed as part of the work coming out of the NCAT test track. And all of the dark or the solid lines that you see to the left are all those perpetual pavements, and they are all below that critical strain distribution, kind of up through the 55th or the 60th percentile. So, and none of them have had bottom-up cracking, none of them have had deep structural rutting, and so we took this as an indicator of success or validation of that endurance limit distribution curve that we developed at the NCAT test track. Now, some of them are very conservative. This section from Iowa, you can see, is well below the curve. The one from Montana is very close to the curve. And again, these pavements were designed a long time ago. We're looking at 30 or 44 years or at the most. And so these weren't designed with this criteria in mind, and yet we're able to kind of see that they all fall at or below that strain distribution. I haven't talked too much about rutting, but the other part of the analysis that Alfredo did as part of this study was to look at vertical strain down in the subgrade layer as a predictor of rutting. And what we found was that it was effective to design at the 50th percentile, or the average value, below 200 microstrain, and every one of those pavements, again, we had different levels of conservatism. The Iowa pavement was well below that. The one that came closest in terms of vertical strain was in Kentucky at 188, but drawing a line at 200 and using a single value there seemed to be very effective and was consistent with what others had found over the years with respect to designing perpetual pavements for rutting. As part of a report, and this has been referenced already during the webinar, but published back in 2015, we ran a number of kind of what-if scenarios, did a sensitivity analysis looking at some different climate zones from cold to hot, Minneapolis, Phoenix, and Baltimore, kind of covering 3 ranges of temperature there, looking at a 6-inch aggregate base pavement and looking at a range of subgrade soil modulus values and base modulus values, came up with recommended total AC thickness required to be perpetual under these new criteria. And you can kind of look in and see, okay, in Phoenix, with a subgrade of 10 KSI, base of 30, we've got 14 inches there. This gives us a general idea. If we look at the furthest column to the right, gives us a general idea of what kind of range are we looking at when it comes to perpetual pavement structures. So on the low end, we're down around, under these conditions, around 8 inches, and on the high, we're up around, I guess, 15.5. And that gets us into the right ballpark. All right, so that covers a lot of the kind of the theoretical underpinnings and a lot of the research that's gone into this new version of PerRoad. For those that are familiar or have used it in the past, the first thing you'll notice in the new version is that we have greatly improved the kind of the title screen. NAPA helped out with that, and I think it has a more professional look to it. The version that we are on is version 4.3. I'll have an address at the end where if you want to download the new software, you can do that. Some new features. The first one on the list is that in the previous versions of the software, we did not allow for traditional ME design. There was some interest, and Trenton really led the charge on this. There was interest in being able to do a direct comparison between a traditional ME design and perpetual. In some cases, you may be just a few inches or an inch or less sometimes away from achieving perpetual status. And being able to do a direct comparison is useful to see, well, if we just invest a bit more here, we may achieve perpetual, and then the math changes a lot in terms of doing a life cycle cost analysis when you have an indefinite fatigue life. Number 2 on the list was we now enable the use of strain distributions, and as I'll show you, we can either enter the values directly or enter strain ratio criteria. We also allow you to control the design on a single percentile value, like I just mentioned with respect to rutting. And as long as we were in there kind of updating the software, we also improved the output format, something that just automatically is formatted, you can put into a report and that kind of thing. And I'll show you all those features. So I'm going to go through some screen captures here. The point of this webinar isn't to make you all experts in running the software, but to kind of point out a few of the changes and show you what's going on in the software. Like before, the software runs up to 5 pavement layers. In this example, I have 3 set up. You can enter seasonal information, and I haven't mentioned this yet, but with the software runs what's called Monte Carlo simulation, which is a numerical analysis technique that allows you to take into account all the variability of the loading conditions, seasonal conditions, material property variability, all the variability that's that we build into a pavement structure. It's able to model that. And so the seasonal information is a good example where we can determine the number of weeks in each of the seasons, what the air temperatures are in each season, and that then kind of helps us derive what the material properties are in that season. Each layer is defined in terms of the material type, and we can specify for AC materials, the PG grade, and so on. So in this case, we've got AC over granular base is layer 2, over layer 3, which is the subgrade soil. And what we're defining in terms of the modulus is the seasonal modulus. So in this case, we're looking at a spring condition, and this is the seasonal, the average modulus in that spring condition for the AC, for the granular base, and for the soil layer. If you click on the variability button, it allows you to simulate the amount of input variability that you have. So whether it's log normal or normal, you can change the amount of variability that you expect in your design, and that is taken into account in the Monte Carlo simulations that are run. Let me back up a couple here. If you click on the performance criteria button within any of the pavement layers, it brings you to the screen where you can define what those criteria are. And what I've got shown in this screen capture is that we're controlling the horizontal strain distribution at the bottom of the AC. And if we click on load default distribution, that'll automatically load basically the tabular data from that previous slide I showed at the 95th, 85th, or all the way down to the 55th percentile. So that essentially is loading in those control points as the basis for design. If I click on load default, I could also just enter them manually if I wanted to. And so that then gives us those control points to be used for design at those very specific percentile values. If I click on endurance limit, this then allows you to enter a value from the laboratory, and if you click on the accept changes there, it then will load for you the distribution that's multiplying by those strain ratios that also came out of that table that I presented earlier. So you basically have 3 options. You can enter it manually, you can use the NCAT default, or you can put in an endurance limit to arrive at the value, or a set of values. In terms of controlling the strain by a single percentile, you can select from a number of different things. Usually we will design on the basis of vertical strain. And so when you do that, you can select the criteria from the drop down there, select vertical strain, and then enter the threshold value, and then put in the target percentile. And the values that I'm showing here on this slide are the default values. They're not default, you have to enter them, but they're what we would recommend based on our research. I mentioned that we also can do a traditional or conventional mechanistic empirical design where we have a transfer function, and so I've just shown a typical function form here where we have the coefficients there shown with the strain. So we've got sort of a K1, which is the 2.83 times 1 over the strain raised to another coefficient. And so if you select this, you can select horizontal strain, put in the threshold value. It'll still account for a threshold strain if you want to do a conventional design. And then you just have to enter the K1 and the K2 values there. So like most mechanistic-based design procedure or mechanistic empirical design procedures, we don't really think in terms of easels anymore. What we think about are load spectra. And so it comes down to defining at the top of the screen general traffic data in terms of traffic volume. If you're doing a true perpetual design using the new criteria, traffic volume is kind of irrelevant. What's important is the percentages of the different kinds of axles that you have, and then the distribution of axle types that you have, which is shown in the bottom table in this input window. But if you are doing a traditional ME or a traditional perpetual design, then the traffic volume does become important because we're trying to predict when damage may occur, when we may hit a critical value in terms of perpetual design. There are defaults built into the software that you can select. The upper right-hand corner here where it says input load spectra by vehicle type, you can click that button and it'll automatically load for you some data. But what happens in the software in the background once you have all this data entered is, as part of the Monte Carlo simulation, it randomly generates loading events. So for example, in this particular situation where we have 50.43% are single axles, about half the time the software will generate a single axle, and then it relies on the load percentages down here to randomly pick based on those percentages how heavy that loading event is. And all of that combined with the earlier variability I mentioned from the material property and thickness data, all of that goes into the strain distribution that we're predicting, and that we're going to compare that strain distribution back to the control distribution as a basis for design. When you come to the output window, for those that have used the software before, there used to be just one output table, and what you'll see now is that there's two, and when you first come into the output window, they're blank because you still have to run the Monte Carlo simulation. But we had to separate those two blocks because if you're doing a traditional ME design, the output is very different, and how you analyze and think about it is very different than if you're doing the new strain distribution design, which I'll show you in a minute. But what you're able to do from this screen is you can again review what you had entered for the design. So in this case, I had chosen 9.5 inches of AC over 6 inches of granular base. And then in the upper right-hand corner, you are able to set the number of Monte Carlo cycles. By default, it is set at 5,000. You can increase or decrease that number as you want to. Once you've set that, you can click on Perform Analysis, and it'll run the simulation. You'll get the blue bar will go across after you're done. And in this case, I've only run a traditional, using the new strain criteria. I'm using the distribution values. And in the bottom table, you can see that we show the layer number. That's column 1. The location, whether in this case at the bottom of the asphalt. The criteria was tensile strain and microstrain. We have our target value. That's the default one from NCAT that I loaded. The target percentile. And then we're simply comparing the actual percentile against the target percentile. And when actual exceeds target, that means we have passed. In other words, if we're kind of thinking about that strain distribution, that graph that we had before, we are at or to the left, or we have lower strains than that design curve would predict for us. And so we can start to look at it and see how much cushion we've built in and so on. And in this case, in terms of fatigue, it looks pretty good because all of them pass, but they're relatively close to, it's not overly done, or it's not over-designed. And then we can look at the top of the subgrade, and here we're looking at vertical strain. And again, we designed for 200 microstrain at the 50th percentile. Our actual percentile was 43%, and so in that case we fail and we need to adjust the design accordingly. So if I go back up to the top left corner, I can adjust that thickness, and in this case I just increased it by a half an inch, and you can see now in the lower right hand corner that improved the overall percentages for fatigue, like compared to what I had before, but it also got me to where I'm now passing on the vertical strain criteria. And so when all these show pass, I know that I have a design that is adequate, and then it's just a matter of, have I over-designed it? Do I want to adjust it? Maybe the next trial I would maybe decrease it by a quarter inch or whatever tolerance you might be designing for. But all that design happens within this input window. The other thing that we can do here is to design, if I redo the analysis and I could design in a traditional ME design. And so what I've got shown in this box is, again, using that transfer function that I showed earlier. Now it's showing some data in the upper box where I have, again, layer 1, bottom of the layer, horizontal strain, and I've got 87.2% below that single critical value of 150. Running the values that go over and above that 150, run it through the transfer function. It calculates for me how much damage may accrue per million axle. And then the last column tells me how many years I have until damage is equal to 1.0, which in traditional or conventional ME design, that is when I would see, say, 25% of the lane area is cracked, for example. So that then tells me how much time I have, and I could adjust these, the layer thickness to get to a number. You know, maybe I'm doing a 20-year design conventional, and I could adjust those values until I see what the, or until I've kind of designed it according to whatever conventional ME parameters that I've decided to set. So this just is an example to compare traditional ME, which is the curve that's increasing with traffic in terms of total AC thickness versus perpetual. And you can see the perpetual is immune to traffic volume because we're designing strictly on the basis of that strain distribution, not on traffic volume. We get a constant thickness of around 12.5 inches or so. And this is, again, for a very specific set of conditions. Minneapolis climate, 6 inches of 30 KSI aggregate base over a relatively soft soil. And the ME pavement, you can see at low traffic volumes, it's around 8 inches, and then it jumps 2 inches when you go to the next traffic volume. Then it crosses over at 500 to where it's thicker than the perpetual, and it just keeps on going. As we continue to add more and more traffic, that line would continue up and up and get into some really outrageous pavement thicknesses. So this is one of the ways that we can kind of look at the trade-off between ME and perpetual, and what should be a natural cap in terms of pavement thickness. In fact, the Illinois DOT uses an approach like this to establish an upper bound maximum thickness for pavements in their state. After you're done running the simulations, or at any point actually after you've run a simulation, you can export the data into Excel. And the formatted output, you basically get a workbook that has a title page as one tab, and then you have all the data that you've input as additional tabs, separate tabs where you have traffic, materials, and so on. You get a performance summary page that can be printed and input into another report that you may be developing for some design, for a design report. It's much more professional looking than what we had previously in the software. So that was a very quick run through of the software, and just kind of summarize here, and I think we will have time for more questions. But hopefully what you've gotten out of this so far is that perpetual pavements are a viable option. We have seen them across the whole U.S. and really across the world, and their biggest advantage is that they eliminate deep structural distresses. The asphalt pavement industry is extremely efficient at dealing with distresses at the top of the pavement structure through night construction, mill and inlay. Those sorts of approaches can be done very efficiently and be very cost effective. Data from the test track, NCAT test track, and from real world pavement sections support using a strain distribution for design. You can now do that within the PerRoad software. It's been validated and it's now fully functional. You can also now do that, or you can do conventional ME design within the software. And what we found is using the new criteria, using kind of typical values when we did our sensitivity analysis, what we found is that the new software gives us pretty reasonable pavement cross sections that are really congruent with where we know perpetual pavements can be achieved in that kind of 8 to 15 inch range. I think we're right on time for questions. I'll also point out here that if you're interested in the software, you can go to the Asphalt Roads, that's the Asphalt Pavement Alliance website. There's a perpetual pavement page there, and you can get to the software download. You're welcome to download it and distribute it. It is a free program, and with that, I'll open it up for discussions.
All right, Dave, I'm just going to read off some of the questions we've received during the course of the presentation. First question is, would you please explain why the strain on the subgrade is taken into account while the rutting is supposed to be blocked by the second asphalt layer?
That's a great question. And Trenton, feel free to jump in as well. So we use the vertical strain at the top of the subgrade as an indicator of really rutting occurring deeper in the structure, down in the granular base, down in the subgrade layer. We mitigate rutting at the surface of the pavement through good mix design or selection of materials. So having higher modulus rut-resistant materials, we should not see rutting in the second and third layer. And in a lot of perpetual pavements, that's the case. We usually, what distortion we do see is at in that top layer.
Yeah, absolutely, because we're trying to protect, the weaker layers below, and just as Dave said, by proper mix selection, proper thickness selection over that weakest layer, which is typically our subgrade, that's what we're trying to ensure that rutting doesn't occur there within the structure that leads to a more costly fix.
All right. The next question is, can the modulus value be input from laboratory testing? If so, which test?
That's a good question. What we have found, so for those that are familiar with the AstroWare software, you're undoubtedly very familiar with the E-star master curve and how that would be generated. What we would recommend to be done within the software would be to use E-star at, or the dynamic modulus of the asphalt concrete at a 10 hertz value. There may be some other thoughts on that, or people may have differing opinions, but what we found to be effective is to kind of use that 10 hertz and then select a temperature that would match up with what you have for your local conditions. So cold climate, warm climate, and so on.
All right, what about SI units, Dave? Can you use SI units in the new version of PerRoad?
Yeah, so currently it does not run in SI. You'd need to convert everything, run it, and then convert it back.
Okay. What happens to the tensile strains at the bottom of the asphalt layer after top-down cracking occurs?
Yeah, that's a good question. So the PerRoad doesn't make an attempt to model that. In reality, as cracking would develop and propagate down through the structure, in reality, you would start to see an increase in those strain levels at the bottom of the structure. What we sort of assume within the perpetual framework is that you're taking care of the top-down cracking before it becomes that severe. So generally, if you're on an 8-inch section and you've got cracks that are at the top 1 inch, what we've seen at the track is that we don't start to see really a change in the bending strain until cracks become more severe, like deeper than that. So this kind of assumes that you've got a rehabilitation schedule that takes care of cracks.
Okay. Right. In the case of using several AC layers, say 3 is in your example in the early slides, is it possible to have a higher modulus for one of the underlying layers, or is it required to have increasingly higher modulus as we move towards the bottom layer, similar to the traditional layered elastic analysis?
That's a good question, and Trenton may have some thoughts on this, but I think one of the things to think about is that having a higher modulus intermediate layer is a good approach because there's not a lot of bending that goes on in that layer. So using things like high wrap contents, other kinds of recycled type approaches can be used to help control the strain at the bottom of the structure. Towards the top, where you do have some, there's more aging that might occur, for example, or you may have some bending strain due to it being located at the surface, you may want to use some softer materials. Trenton, do you have some thoughts on that?
Well, one of the things that we've seen when we've actually done lab testing is like our premium material, the SMAs. In a lab, it would show soft, but in reality and in performance, it's greatly exceeded. So trying to balance that all and doing a mechanism type model doesn't work as well, but in reality we know that that is a great upper surface. It goes back to that earlier diagram you showed from Dave Newcomb in 2001. But having that strong rut resistant layer, especially as we're seeing really changes in the types of vehicles and the tire forms that with more of the wide bases being used, having that rut resistant stronger layer, being able to model it proves why in those cases wrap's not a bad thing if we have a good mixed design and we meet all the mixed properties.
All right.
One
Another question for
you missed, Amy, was
with
the fatigue endurance value. Is that from a 4-point or an SVECD approach?
That is from the bending beam testing.
Right. All right, very good. And we've got quite a few more questions, so I'll just say, Dr. Tim, are you and Trenton available for maybe 5 minutes after till 2:05?
That's fine with me.
Yeah, I'm good.
All right. Okay, so we'll work on through these. What is the minimum layer thickness that the software can take? For instance, in AASHTO, where there's a limit of 1.5 inches for AC, if I'm not mistaken.
Yeah. So and I haven't thought about that question in a long time, but I think it's 1 inch is the thinnest you can do, and really the software is more limited by the fact that you have only 5. You can only simulate up to 5 layers. So if you're doing a very complicated structure that is changing a lot with depth, you're going to have to probably group some layers together, much like you do in the MEPDG if you have a lot of pavement layers. But the thinnest you can do is 1 inch.
All right. Where is AASHTO on accepting the endurance limit design concept?
That's a good question for Trenton.
Wish I could tell you. I'm not aware. I'm not on the task force anymore. I know the way the software was originally set up, there was a desire to have a single value, but as Dave went through, there is not a a silver bullet, one number and then you're good, because with the way Pavement ME works, it calculating stresses and strains throughout the year, and as material properties changes and the loadings changes, so it's not a single value. So as far as AASHTO adopting one, as Dave pointed out, lots of publications and research done on a variety of numbers, but frankly I'd be surprised to see AASHTO adopt a single value for use because of all the complexities and differences across the country.
All right. Is there an updated user manual?
Yeah, so the help file was updated that accounts for all of the changes in the software. The biggest limitation with that right now is that it does not run in Windows 10. if you have anything prior to Windows 10 and you try to access the help file, you'll get a little message will pop up. If you follow the links to Microsoft, it'll install a patch for you. I'm still working with trying to figure out how to make it fully functional in Windows 10. We have a few different ideas on that. So.
Okay. What is the usual time interval for surface maintenance of perpetual pavement?
It's around, what, Trenton, 15 to 16 years is the kind of average number across the country?
Yeah, I would say, depending on where you're at, anywhere from maybe as low as 13 to 18, and there's some I've seen that's upwards of 20 years, again, depending on the materials and the climate. But I'd say 20 is probably at the upper end for a lot of these perpetual pavements. But we just get into a mill and resurface type of scenario, highly cost effective.
Absolutely. And I can tell you on our end, the awards that have come in when we review those, you know, there'll be anywhere from 12 to 15 years to 20 years, to your point, Trenton, just depending on, you know, all the factors that go into that. Next question, how well do you think the NCAT strain distribution will correlate nationally? Will the strain distribution need to be calibrated at the state, regional level?
Well, what we're able to find from the Perpetual Pavement Award winners is that we think it worked well for all of those states that we looked at, and that covered a number of climate zones and a wide range of traffic. So I think for the short term, I think it's a good value that has some conservatism built into it. There may be a need in the future to, you know, as states consider adopting this or whatever, to look at pavements in their own areas. They may want to refine that, but I think it is giving us it has been validated on a wide range of pavement sections.
Very good. And what is your experience in back calculation in perpetual pavement?
We've done that on the sections at the test track, and really it's no different in terms of how you back calculate versus conventional pavement. They, you know, typical challenges you run into, but in the past I haven't had to back calculate them differently than conventional pavement structure.
Okay. All right. And we'll take a few more questions to 2:05. We've got about 3 more minutes. Dr. Tim, what is the temperature of the FEL value introduced in PerRoad? Because the software only asks for one value. What is it? Okay, it's the question repeated. So that's the question.
Yeah. So what using the strain distribution does is it's meant to cover the range of expected strain levels in the pavement due to a number of factors, and one of those factors is temperature. So it's kind of what is the working range of that pavement due to temperature, due to loading condition, due to all the different factors that come into play. So we really need to get out of the mode of thinking about one test or one set of tests in the laboratory at one temperature and into this idea of we're really trying to look at the entire range of temperatures. Now, what's run in the laboratory in the strain ratio that we apply, that is run according to the test standard. I think it's 20 degrees C, and then we multiply by the ratio values to get to kind of the whole spectrum of strain levels.
All right. The horizontal strain is in the high modulus layer and fatigue resistant layer, or only in the fatigue resistant layer?
So the designer can make that decision. What typically is done is to look at just the bottom of the asphalt layer, but if you are putting in let's say you have a very stiff material that you have concern that cracking could originate there if the strains are too high, the designer has the option of putting in basically putting a strain distribution in on that layer as well, and could analyze it. So that capability is there.
All right. This one I really want you to answer. If perpetual pavement survive for 15 to 16 years, and how can one justify its use compared to rigid pavement?
So the 15 to 16 years is not a survival number. That's how many years until we have top-down cracking that we. So that's not a reconstruction. That's not a deep rehabilitation. That is a surface basically a surface improvement of the sacrificial layer.
Yeah, think of it this way. It's not, at 15 years or so, we're doing a functional restoration, but not a structural restoration, because again, we're designing to ensure failure from the bottom up is not occurring. So like the roof on a house, eventually the shingles wear out. The house is still standing. It's perfectly sound. We're just replacing the shingles. The same with perpetual pavements. We're making sure the foundation is solid. And then as cracking or as roughness increases over time, we're just replacing that top layer and putting in a new layer. And then we're out of that road again for another 15 plus years. So it's very economical. You got to just keep separated functional life from a structural life.
Yeah, absolutely. There was another question that asked also about consideration of rigid versus flexible pavement when you're doing perpetual pavement design. And I think you just hit the nail on the head, Trenton, that this really does offer an economical sort of solution for your pavements, because you do have a very valid sound structure. You're just really just coming back and addressing the top, or the shingles as you put it. So this is our last question. I'll just say I've seen a lot of your requests for PDHs, and we will make sure we get this out. So this will be our last question for the day. If you have any more, you're welcome to email me at amiller@asphaltroads.org, or if you have Trenton or Dr. Tim's email addresses, you're welcome to reach out for them as well. So the last question is, why relate perpetual to years and not to traffic? In Brazil, we have highways that reach 200 million easels in 5 years. We can apply perpetual concepts to these highways.
Yeah, so when you get into this idea of perpetual pavement and that you're limiting the bending strain, for example, below the threshold, the number of repetitions becomes irrelevant, as would the amount of time, because you just aren't inducing enough strain for it to initiate a crack. There's not enough bending energy going into that pavement for a crack to initiate and propagate to the surface. So what becomes really important under those conditions is how heavy are the trucks, how heavy are the axles, and so on, but not necessarily how many of them do we see. And so it's kind of back to the idea of bending a paper clip. We're just trying to design it in such a way that we're keeping it below some critical level. And if we do that, then that 200 million, if it was in 5 years or 10 years or 50 years, that number is kind of irrelevant. It's really based on how heavy those trucks are, or those axles.
All right, very good. Well, thank you so much, Trenton. Thank you so much to Dr. Tim for your time today. I think it's been very informative. We had lots of attendees today, so your presentation was very popular. And once again, thank you all for spending your time, a little bit of time this afternoon with us, going through this. If you have any questions, please, again, you can find my email address on the Asphalt Pavement Alliance website. If you have any further questions, we'll get them answered and get back to you. Have a great day, everyone.
Thank you.